Alright, let's try learning a little bit about physics, kind of from basic principles. And in this particular video series, we can try using a little bit of calculus, pretty basic stuff, just to derive some of our basic equations, and get to thinking about the world. Okay, so we want to think about the world. Well, what is the world? It is Earth and sea. This is my quick drawing of a globe. Maybe it's the moon orbiting the Earth. And physics describes how the moon orbits the Earth, how the Earth orbits the sun, or things like Isaac Newton discovering why the apple fell from the tree and hit the ground. Using physics, we can figure out how fast the velocity the apple was moving when it hit the ground. We can figure out the time it took for the apple to hit the ground. We can do, if we have this information, then maybe we can figure out the distance it took between the apple starting and the apple hitting the ground. So there's lots of stuff that we can do with physics. Okay, so the first thing we have to do to think about physics is figure out how we would describe the world through equations, because we need physics equations that we can just plug in to different situations in the world and thus figure out things that might be happening. So let's say we have a one-dimensional world. This box is resting on this number line, for example. At an initial time 1, it's at the position x1, and maybe at some time 2, it's at the position x2. We want to figure out how fast this object is moving. How would we do that? Well, we could figure out how much distance the object had to travel. That would be x2 minus x1, and we want to figure out how much time it took to travel that distance. That could be t2 minus t1. That's basically like saying velocity, the speed that an object is moving in a certain direction, is equal to the change in distance over the change in time. Got some stray marks there. So it's equal to change in distance over change in time. Something like miles per hour, kilometers per hour, meters per second. Things we're all familiar with already. Or if we want to use calculus, which will become very useful to us, we can say that velocity is equal to dx dt, the infinitesimal change in distance over the infinitesimal change in time can describe exactly the velocity of any object. So that is the first thing perhaps that we can do with physics, and just making up a description of the world and figuring out what we can do with it. We've already got something very useful. Okay, so I just cleaned up the board a little bit. Velocity is the change in distance over the change in time. Now, do things always move at a constant velocity? That's not really true. Think of yourself in a car. You start at stop, you press on the gas pedal, and you start to move forward. After 1 second, you're moving maybe at, a meter per second. After a couple seconds, maybe you're at 10 meters per second, and you're increasing your speed over time. Or maybe we'll use miles per hour since that's more familiar. At first, you're at 0 miles per hour. Then maybe after 12 seconds or so, you're at 60 miles per hour. So if this box, say somebody who's pushing on it, started at rest, it would start to accelerate to the right because somebody's pushing on it. Some constant force, giving it some constant acceleration. Then after t2, maybe it reaches its final velocity. We stop pushing on it, but we're interested in how fast the object might be moving, how acceleration is related to all this. So, what is acceleration? Well, acceleration is going to be equal to the change in velocity over the change in time. So if we're thinking of something that may move at 1 meters per second, if it's accelerating every second it goes faster by 1 meter per second, then acceleration might be described as something going 1 meter per second every second increases its speed by a meter per second. Okay, so we have then acceleration, if we put it in calculus terms, is going to be equal then to dv dt. So we've got two equations now that are pretty useful. V equals dx dt, A equals dv dt, dv dt. Okay, so now I put it in calculus terms. A equals the infinitesimal change in velocity over the infinitesimal change in t dv dt. Alright, so we've got some mathematical equations. Let's see if we can do anything special with them. Let's rearrange. So A dt is equal to dv. This is a calculus equation. If we integrate both sides, we can see what we get. So A with respect to t is going to now be A times t. We'll integrate from 0 to t. Over here, we'll do it from v1 to v2. It's going to be equal to v2 minus v1 when all is said and done. So then we get our first kinematic equation of motion. Say v is equal to v naught plus at, or I could say v2 is equal to v1 plus at, or however I want to do it. Okay, so I've now redrawn the box problem and put some numbers on here so we can try to do some physics using that first equation that we derived. Alright, so let's say the box here started at position 0, ended at position, we don't know what position it ended in, we'll figure that out later, but it was accelerating at 5 meters per second, and over 2 seconds we want to figure out how fast it was going, what was its velocity. Later on we'll figure out what position it was in and all that good stuff. So v equals v naught plus at. That's our equation right here, equation 1, the first kinematic equation of motion, if you want to call it that. Now we know that v naught was 0, it wasn't moving at the start, so it's actually equal to at, and we can fill this in. Acceleration is 5 meters per second times 2 seconds is equal to 10 meters per second. So that is the box's final velocity after 2 seconds. If we want to figure out how far it traveled, remember that velocity is also equal to distance over time. The change in distance over time we did before was dx over dt, velocity dx dt. Well, the distance again it traveled we don't know, but we do know the velocity and we do know the time. Right? Is it velocity equals 10, time equals 2? Well, not exactly, because it started at time 0, but since it was a constant acceleration, we can say that the average velocity is going to be equal to the velocity final minus the velocity initial divided by 2. That's just an average. At one time point, at the end, it was 10 meters per second. At the beginning, it was 0 meters per second. So the average velocity is equal to 5 meters per second. That means that 5 meters per second times 2 seconds is going to be 10 meters traveled. So I can go ahead and fill that in here as position 2 is at 10 meters. But this is a little squirrely stuff. Like, maybe you don't trust me on the average velocity of something being the final velocity, its initial velocity, dividing by 2. Maybe that doesn't make enough sense. It's something that works when you have constant acceleration, but only if you have constant acceleration. If we were accelerating at 2 meters per second for the first few seconds, then we accelerated even more, pressed harder on the gas pedal, then maybe that wouldn't be true. But it is true for this. Nevertheless, we can derive a second kinematic equation of motion and prove that the box did indeed travel 10 meters. And we'll do that in the next video. Alright. So what about this tree over here that I've drawn? Is there anything we can do with that? Let's say we have this apple. All of a sudden it fell from the tree. It maybe took, let's say 3 seconds. And we want to figure out how fast the apple is moving after 3 seconds before it's hit the ground. Maybe this is a tall tree or something. What do we need to know? So v equals v naught plus at. Again, v naught is going to be 0. So v equals at. And we know that the time is 3 seconds, so it's a times 3 seconds. What is a? Well, on Earth, everything is going to accelerate the same, whether you drop an apple, or a feather, or a bowling ball. If there's no air resistance, there's nothing getting in the way of something like a feather, then objects drop at the same rate of speed. And we commonly write this acceleration due to gravity as g. And g, acceleration due to gravity, is equal to 9.8 meters per second squared, or one can just round and say it's equal to 10 meters per second squared, or meters per second. That means that the velocity after 3 seconds for this apple is going to be 30 meters per second, 10 times 3. So already our first kinematic equation of motion can do a lot for us, but there are more equations to learn, more stuff we can do just with basic knowledge of physics and a basic mind thinking about how we might describe situations on Earth in terms of equations. So thanks for watching this first video, and we'll do a second video shortly to explain the second kinematic equation of motion.